Hi guys. Yesterday we were finishing up with these even odd properties and talking about how they exist because of what we understand about even and odd functions and symmetry across axes and stuff like that. Now, when I guess and I didn't tell last class this, but I think the best thing to view, and it makes a whole lot more sense, I think, in regards to which ones are even and which ones are odd, when we look at the sine curve or the cosine curve, for the mere fact that if I look at the sine curve, let's just do this real quick. Come on. All right, so if I, let's just say in this green box, put in cosine of x. Looks like that, okay? Now, in the second graphic here, I'm going to type in cosine of x for x being greater than 0. Just that stuff there, okay? So if I kind of zoom out a little bit on both these, would you guys agree that if I took this curve, this red curve right there, and I reflected it across that line right there, do I get the same as this green curve? Okay, so what that means, if I reflect across the y-axis, that means it is an even function. Does that make sense? I have y-axis symmetry as an even function. So if we go up here, it says cosine and secant are your even functions. Does that make sense? Because they are the ones that are symmetric across the y-axis. The other ones are odd functions, so let's talk about an odd function real quick, seeing that visual. So that's talking about the sine of x. So it's that curve. Oh, I wanted that in that one. So sine of x. Okay, is that curve there. Now, if I take over here and graph just sine of x greater than 0, okay, and now I reflect that across the y-axis, it's just going to give me a little bump right here, correct? That makes sense? Is that going to mimic this? No, okay? So I need to reflect it across the y-axis and then reflect it across the x-axis, okay? But if you remember, back to geometry, if I take that curve and rotate it, I need to put a point in here for the origin. 0, 0. Okay. So if I take this curve, rotate it there around the origin. Now it doesn't matter clockwise or counterclockwise, but I'm going to rotate it. Let's just do this. Let's put A in there so you can see it actually happening. And we'll change that property to 180 degrees. If I rotate that thing 180 degrees about the origin, does that end up giving me that curve there on the left? Okay? So a rotation around the origin 180 degrees is exactly the same thing as saying it's an x-axis reflection followed by a y-axis reflection, or vice versa, a y-axis followed by an x-axis. And that means that we have symmetry across both axes. And usually we call that an odd function. Does that make sense? The way I remember that one is an odd function starts with O, symmetry across the origin. Origin starts with an O, right? Okay, or reflection across the origin. Okay, so that's why they're referred to as even odd properties. Okay, and so if I'm looking at then, let's just deal with the sine of negative t. If I'm looking on, and we go back and look at the unit circles with this as well in a moment, If I'm looking at sine of negative t, let's say I'm going sine of negative, let's just say pi over 6, and I want to make that an asymptote, or not an asymptote, but a vertical line. So I'm looking this curve here, okay? And essentially I'm looking then, the sine of negative pi over 6 is going to be the y value of where that curve and that curve, or that line, intersect. Come on. Be that point right there, point E. Does that make sense? Okay. Now, that y value ends up being negative 0.5, right? I'll zoom in a little bit more on this. How does that relate to, so that was the sine of negative pi over 6. Let's look at sine of pi over 6. We'd be looking at the y value of that point F. Okay. Let's see here. Not F. What is this line here? Oh, hold on a second. Let me rephrase this. Make it a little bit easier to think about. So we have sine of x, okay? I want to evaluate, so x equals pi over 6, or x equals negative pi over 6. I think this is going to generate the values a little bit easier for us to realize. So that is sine of x gives me that curve. If I were to ask the sine of 0.52, it's going to give me that number right there, right? That y value. If I ask for the sine of negative 0.52, it's going to give me that y value right there. Does that make sense to everybody? Okay. What is the difference between, I don't know why this thing's doing this to me, that and that. There we go. That and that. What is the difference between those two y values? Okay, so you did the subtraction. What is the visual difference between those? One is negative, right? Okay. So how I make them equal? Multiply one by a negative, right? Does that make sense? Okay. Now that occurs, that exists no matter what I use. So I use pi over 6, right? Let's go pi over 8. And negative pi over 8. Are those two numbers the same, except for one is opposite? Right? So it doesn't matter what my input value is, what my argument is. To make them the same, I need to multiply one of them by a negative. What we like to do is usually not deal with a negative angle. So here they're saying if you have sine of negative t, instead of having to deal with a negative angle, we would much rather prefer to deal with a positive angle. But we can't just allow it to become positive. Does that make sense? Okay, because we've changed things. How does it change? We need to bring that negative out in front, essentially. Okay, is that all right with everybody? If you think about the unit circle, what that means, because you're going to find out that this curve here is directly related to the unit circle. Okay, it comes from the unit circle. If I'm looking at the unit circle, if I'm interested in sine of negative pi over 6, now my applet here won't convert it to a negative, but you guys agree that 330 degrees counterclockwise is the same thing as negative 30 clockwise? So that would be negative pi over 6 right here, right? Okay. The sine of that is negative 1/2, right? if I look at sine of 30 degrees or sine of pi over 6, the y value of the sine is 1/2, right? Well, how do I make those the same? I negate the positive one, right? Does that make sense to everybody? Okay. And that exists all the way around the unit circle. It doesn't matter what angle I'm interested in. If I'm interested in, let's say, negative 2 pi over 3. So negative 2 pi over 3 would be that right there. Does that make sense? Okay. And the sine value is negative radical 3 over 2. Okay. So that's the sine of negative 2 pi over 3. Well, the sine of 2 pi over 3 is that number right there, right? Okay. Well, how do I make those two numbers that have boxes around them equal? Is that I negate this one, and now those two values, the opposite sine of 2 pi over 3 and the sine of the opposite of 2 pi over 3, are now the same thing. So it doesn't matter where you're at on the unit circle. Does that make sense? Okay. And the task of that, guys, is the reason we have that even-odd property, or that we talk about it, is because it allows us to quickly transition from an argument of value in the parentheses of sine, cosine, tangent, secant, cosecant, cotangent, and turn it into a positive value instantaneously. Okay? And why is that? Now you're saying, well, why do I need to do that? If I have sine of negative 2 pi over 3, I'm just going to add 2 pi to it, and it's automatically going to turn it positive, right? Well, eventually we're going to take that negative 2 pi over 3, and you're not going to know what it is. It's going to be your variable, okay? And they're going to make it negative. And now because I don't know what it is, I can't just add 2 pi to it. Does that make sense? Because I don't know how negative it is. Is it more than, negative 360 degrees or more than negative 2 pi? So how many multiples of 2 pi would I have to add to it? We don't know that. So if I want to generate an expression so that negative angle, that negative argument disappears, this would be one of the properties that I use to do that. Okay. The cosine is a lot simpler. The cosine says if I have the cosine of a negative argument, that is exactly the same thing as cosine of the positive argument. There you do not have to negate them. For the instance or the reasoning that if I have, again, let's go cosine of negative 2 pi over 3, that value ends up being negative 1/2, right? Okay, it's that value right there. Well, then how does that relate to cosine of 2 pi over 3? Cosine of 2 pi over 3 is that value right there, which is negative 1/2. Do I need to do anything to these two cosine values to equate them? They're the same already, aren't they? Where the sine one, we had to make one of them negative, correct? Okay. So in the cosine one, they're already the same, so I don't need to negate either of them. I then know that cosine of the opposite of 2 pi over 3 is the same thing as cosine of 2 pi over 3. Therefore, regardless of what my t value is, that statement is always true. Okay. Anything about it, if I'm starting at the origin, I'm starting at 0, 0. To get to both those points, don't I have to move in the same x direction? Yeah. Okay. To get to the y values of certain points, I don't move in the same direction. I move in opposite directions. Okay. So that's kind of the concept behind those two even-odd properties. Now, this is something that I hope you can convince yourself of, and you've heard me talk about it in college algebra. You obviously heard me talk about it a lot in geometry. You go back to geometry, there's a lot of junk that was provided to us in geometry that we had to know and had to keep and retain and be able to then You know, if I learn it in Chapter 3 to allow that to resurface in Chapter 7 to talk about maybe 1 or 2 problems out of a homework assignment, and then it goes away until I get to Chapter 11 again, right? And we had to retain that information and had to be able to regurgitate it whenever it was necessary. That same thing's going to happen in trigonometry. And there's a lot of things that we have to remember. And your memory is going to fail you, correct? Whether it be the short term or long term, and that's all relative. It might, you know, short term might be 3 years, okay? Or you might think that'd be long term. Whatever it may be, at some point your memory is going to mess you up. So my hope is that as we go through these things, you develop relationships so that we can, if we have to memorize things, we can memorize the most minimal amount of things, okay? And then understanding our relationships will allow us to take place of all that other memorization, okay, or need for memorization. So here's what I'm talking about in regards to that. If I look at this sheet right here, okay, this sheet, this is a Word document of pretty much, I don't want to say all, but a good portion of the formulas and things called identities that we're going to have to commit to memory at some point in this course. Okay? Is that a lot of stuff? And if you look at these, I mean, look at these. These are called our sum and difference formulas. Look at these things. Are these very similar? These 4? Okay? If you tried to memorize those, you're going to mess them up. Okay? So as we get to that stage, I'm going to show you relationships that allow you to learn one of them, or maybe to learn just the concept of one of them. It allows you to generate that first one, and then once you generate the first one, you can then generate all the other ones off of that. Okay? That's kind of what I want you to see here with these even and odd properties, and that's kind of what I want you to start trying to program your mind to work like, so that when we get to those that are more, okay, here, if I know those 2 that I've got in blue, I should know the rest of them. And I think we finished on this one yesterday, but I want to make sure that we do talk about it. Talk about the tangent, okay? If I want to figure out what the tangent of a negative angle is, I don't want to memorize it, okay? But I do know that tangent, in terms of sine and cosine, is what? Sine over cosine. So tangent of negative t, the only way that I could get that is to take sine of negative t divided by cosine of negative t. Does that make sense to everybody? It's a negative there. If that's the case, what did we just say sine of negative t? Right, I bring that negative out front, right? Because my goal is to get rid of this negative t, to make that turn into a positive t for tangent. So these 2 arguments somehow need to turn into a positive t, right? Cosine of negative t, we just said was cosine t. Now that both those are the same argument, I can actually do that division. What is sine divided by cosine always going to be? Tangent. And now we've converted a negative angle to a positive angle. And if I take a negative divided by a positive, this result is negative. So that is how we get from that to that. That is why that's true. Okay? Now we could go back to the graph of the tangent function and look at the, kind of like we did at the beginning with sine, look at the negative pi over 6 and positive pi over 6, and you're going to see that the y values are opposites of each other when they intersect those 2 lines. But that right there is a algebraic proof of why tangent of negative t is equal to opposite tangent t. Okay? One of the greatest byproducts, I think, of learning trigonometry, not just to learn the triangle information, but it practices your algebra, and it allows you to become very skilled. If you devote yourself to it, becomes very skilled at the algebra that is incorporated in doing a lot of proofs of writing why formulas are what they are, like proving the quadratic formula, proving the distance formula, proving some of these relationships, okay? You need a good amount of algebra skills to do that stuff, and trigonometry kind of forces you to kind of hone in on those skills. Cosecant's the same way. If I take cosecant of negative t, well, cosecant is 1 over what? Sine, right? Just so can I do that? All right, so then sine of the opposite of t is just that, and that substitution right there, making that turn into this, change the negative argument to a positive argument, and that's what we want. Okay? But what is 1 over sine? Cosecant. So in these kind of little proofs, what we're doing is we're undoing or we're getting rid of the cosecant, writing it in terms of its reciprocal, which you might think is kind of redundant or unnecessary, because then we go back into that reciprocal, right? We go from cosecant to 1 over sine, and then we go back into cosecant. And you're thinking, well, why do we do that? The reason we have to do that is so that we can transform that negative argument to a positive argument. Okay? You do the same thing with secant and cotangent. So my hopes are, guys, is that you don't remember all 6 of those. You learn these 2. Okay? And if you're kind of real good at kind of organizing things in your mind and developing relationships, maybe just learn that one. And so I learned that one, and then I learned, well, the sine one is the same, except for I put a negative in it. Does that make sense? If you can remember that stuff, it allows you to now know 6 pieces of information by just knowing 1 piece of information. I think that's a very easy piece of information right there to commit to memory. I think develop, as you guys get into, I don't know if I said this yesterday, as you get into more and more college classes, obviously the material, the content in those classes is going to become, no matter what area you're in, that the material gets much more difficult, much more involved. It's more, I guess, quickly paced, and you're going to have to force yourself to develop relationships instead of just trying to memorize everything, right? And that's what they try to force you to do in college. Memorization is a very, 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 very low-level learning skill, okay? Anybody can memorize things, right? Okay? You've all seen, like, those 3- or 4-year-old girls on Oprah or something. They ask them, what's the congresswoman from Utah's name? And they instantly know, right? Well, that's memorization. Anybody can do that, okay? It just takes time to learn it, right? To drill it into your mind. You guys were all told and you learned the state capitals and all that kind of stuff, right? But when was the last time you knew the state capital of South Dakota? Probably since the last time that you learned that, right? You probably don't know it anymore, right? Okay? So that's what I'm trying to prove to you, trying to show you that you're going to forget some of that stuff, okay? But if we force ourselves to develop relationships, I think you're going to remember it a lot better. So why are we doing this? Like I said, the purpose of this is to do something like this. If I sine of negative pi over 6, we have the ability to say, okay, add 2 pi to that, and it becomes a positive angle. That's one approach to doing this, okay? The other approach is to use the identity that we just said. If I'm using the sine of a negative angle, that is exactly the same as the opposite sine of that angle, but making it positive. And now the hopes are that we know what the first quadrant looks like, and we know what the sine of pi over 6 is. What's the sine of pi over 6? 1/2. The y value for pi over 6 is 1/2, and if I negate that, I get negative 1/2, right? So if you were typing your calculator, sine of negative pi over 6, make sure you're in radians, it's going to spit back negative 1/2 to you. Okay? The overall goal, though, is to remember that in an equation, I might not know what this is. I might not know what that thing there is. It might be sine of negative theta. Okay, and I might, in my equation, have other objects in there that are like maybe cosine of positive theta. We're going to find out that we cannot do anything nice with those things. Okay, or maybe I had something like this. Maybe I had, let's go, plus sine of theta plus x equals maybe 5 or something like that. So they had an equation like that, okay? I can't do anything. Some people might say, well, that's 2 sine theta. Well, I can't do that because one is negative theta, the other one is positive theta. Does that make sense? So what I can do, though, is rewrite this first one as the opposite of sine of positive theta. That's a true statement now, right? Plus sine of theta plus x equals 5. What's nice about that? Yeah, I just solved that and got x to be 5. Okay? So that might be, and now that's kind of an elementary equation, and I structured it on purpose that way. But that's an example of how we could use these properties to make life later on in other aspects of this class a little bit easier. Okay? Now, a lot of times, guys, those identities, if I'm talking about the even odd ones, sometimes they're called your negative properties. Okay? In regards to the identities that we use, they're probably least used, but they do show up occasionally. Okay? And so it's important to be able to recognize them. This cosine of negative pi over 4, okay, that should equate to cosine of pi over 4. The rule said the cosine of a negative angle is equal to the cosine of that angle, but positive. So what's the cosine of pi over 4? Radical 2 over 2. Okay, so that's what we're looking for on that one. Is that something we can do, guys, with those things? Okay. Obviously, you got your unit circle. You can use your unit circle if you feel like that's better for you. I would try to learn that concept that I just gave you, though. So if I go negative pi over 4, I'd be there. Okay, I'd be tracing out from here to there in that direction. Is the cosine of that radical 2 over 2? Okay, but we just found it by actually looking at that angle instead, which is, I think, a little bit better for us. Okay, I'm a strong believer, guys, that this class does get hard. Okay, but my belief is the more time that we spend on these small, fundamental kind of building blocks, the harder stuff alleviates itself quite a bit, makes itself a little bit easier. I have students that do this all the time. You know, every year I get 4 or 5 students to be in chapter 9, and they don't know that cosecant 1 over sine. So they're trying to learn stuff in chapter 9, new information that is using old information when they don't know the old information. So they're learning 2 things at the same time, trying to learn 2 things at the same time, and they're not getting either of them. Okay, so this stuff is very, 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 very important. Okay, these are referred to as reciprocal identities, sometimes referred to as at least your tangent and cotangent ones. A lot of times are called quotient identities. Okay, because you're dividing. The idea of an identity, and I'll show you this with Desmos here in a minute. The idea of an identity is that you have an equation, and each one of those is an equation, right? Each one of those phrases up there is an equation, that no matter what you plug in for your variable, the left-hand side is always equal to the right-hand side, no matter what the variable value becomes. Okay? So, you know, if I want that first one, cosecant of t, if I want t to be 100, put it in as 100, and that will be the same thing as 1 over sine of 100. Okay? If I want to put in 0.145, cosecant of 0.145 is exactly the same as 1 divided by sine of 0.145. Okay? It does not matter what t is. Those 2 things are always equal. Okay? So that's what we mean by the phrase identity. And you're going to hear me say the word identity all the time in this course. That's what I'm thinking about. Okay? That's what I'm trying to reference you to, is an equation that is always true. Why is that nice? Why is it nice to have an equation that's always true? Through my work, I might end up having something that looks maybe kind of like this, where I've got, let's So we got the cosecant of t times the sine of negative t. And I want to go through this, and I want to make this thing look a little bit simpler. I want to, in my equation, this expression is causing me some issue. All right, well, I'm going to do substitutions. Okay, that's what identities ultimately do for us. Okay, the first thing I would do is use what we talked about in the even odd properties, is first get these to both have the same t value, right? Can I do that? It's kind of a substitution, right? Okay. Now what I would do is say, okay, well, cosecant is the same thing as that, right? Can I make that substitution? Can I say cosecant is 1 over sine of t? Multiply that by negative sine of t. I'm going to write negative sine of t like that, hopefully prove a point to you. What are those two factors? They are what to one another? Other than the plus or minus, are those multiplicative inverses? They're reciprocals, right? So what are they going to multiply together to give me? 1, but one of them is negative, right? So that blue thing, because of our identities, that blue thing is actually negative 1. Okay? And that's kind of the purpose of having identities, to see where we're taking this stuff, is to make, ultimately, equations a lot simpler for us to mess around with, to solve and to manipulate. Okay? So cosecant is 1 over sine. Now, something you don't see a whole lot in textbooks, but we do use it, is that cosecant of t equals 1 over sine of t. If I multiply both sides by sine of t, I get cosecant of t times sine of t equals 1. And then if I divide both sides by cosecant, I get sine of t is equal to 1 over cosecant of t. Does that make sense, everybody? So you see how they're kind of expressed differently. That one's solved for cosecant. The one on the bottom right is solved for sine, right? But they are reciprocals of one another. So 1 over sine is cosecant. 1 over cosecant is sine. Is that all right, everybody? And you can do that with all of those. Okay, so secant is 1 over cosine, but 1 over secant is the same thing as cosine. Okay, 1 over tangent is the same thing as cotangent, but 1 over cotangent is the same thing as tangent. Okay, and we can do that little game with all those. The reason that they don't show you those in a textbook is because they're assuming, the author is assuming, that you understand some of your Algebra 1 concepts, and if you've got these two things as reciprocals, we can look at either one, cosecant or sine, solve for, okay, in terms of the other. All right. Now, let's talk about why, like I said, why they're identities. And then let's start with the most basic, fundamental type of identity that you've seen in the past. If I type in, let's just go, let's say I'm looking at this equation. Let's say 2a, I think in last class we did 2a plus 6 equals 2 times a plus 3. Understand, because of the order of operations, when I choose an a value, I'm evaluating the left-hand side differently than I'm evaluating the right-hand side, correct? Okay. A is, let's say, 3. On the left-hand side, I take 2 times 3 plus 6. If a is 3 on the right-hand side, I'm taking 3 plus 3, and then multiplying that by 2, right? So the order of operations, the substitution there is different. So let's say that I have 2a plus 6 on the left-hand side. I'm evaluating that for a. If a is 1, there you see I get 8. And if I do 2a plus 3 on the right-hand side, a is 1 again, you see I get 8. So here's the left-hand side, here's the right-hand side, here's the input value that I'm going to use. What do you notice about your two results? They're always the same. No matter what I do, no matter what I input on the left and what I input on the right, as long as the input is the same, the results are the same, right? That's an algebraic identity, okay? Saying that no matter what you choose as your input value, you get a true statement, okay? So let's talk about your cosecant and sine identities. Now, this is the reason I like to use Desmos is because your TI-8384 doesn't have the cosecant button on it. Okay, so you wouldn't be able to truly recognize this relationship using the functions on that calculator. And secondly, my calculator doesn't work. So if I type in cosecant of t, okay, I get that. If I type in 1 over sine of t, I get that. No matter what I choose, am I getting the same results back every single time? Yeah. Okay. If we go to the tangent of t, we said in the description that it's the same as sine of t divided by cosine of t. No matter what I plug in, are the results always the same? Okay, that relationship, that identity concept, guys, is pivotal for this course. All right, let's talk about these last three. Okay, these last three are very similar. And I told the last class, if you were to come into class today at, when did you actually get here? What time? Yeah, what time does class start? Okay, 9:04, 9:05, 9:06, whatever. You come in here and you ask me, Mr. Fay, what are the three Pythagorean identities? No, I don't know. I've been teaching this thing for 12 years. I've been using it since I was your age. I don't know what they are. Okay? And the reason I don't know what they are is because I learned early on when I tried to memorize them, in that middle one, I always put cosecant where it says secant. I always, in that last one, I always put secant where it says cosecant. Okay? And I got the tangent and cotangent stuff messed up too. I always screwed them up. Okay? So I don't memorize them, but I know how to generate them when I think I need them. Okay? And really the thing is, guys, that when do I know or when do I think I'm going to need them? When I start seeing tangents, secants, and cotangents squared in my problems, that's when I think I'm probably going to need these things, and I generate them real quick on my paper and then see if they're going to be useful. Okay? And the generating of them is very, very quick. Now, the first one, I memorized that. Okay? But you shouldn't have to memorize it because you already know it from some relationships. Okay? What is the equation of the unit circle? Thank you. X squared plus y squared equals 1. So if I were to get our axes in here, type in that equation, x squared plus y squared equals 1. Okay, so we've got that circle. Any point on that circle then is an x, comma, y, correct? But on the unit circle, okay, we have also figured out, because of how, that value is 1. Okay, this is your y, this is your x. If I know this angle of, let's just say, theta, then isn't that number right there the same thing as the cosine of theta? Isn't that number right there the same as the sine of theta? Those two things are equal. So you just told me x squared plus y squared equals 1 was the equation of this circle. But if we know that x is the same thing as cosine theta, can I do this? X squared, so I'll put cosine theta in. I'm going to square it. Add to it now y, but y is sine theta. Put that in. Square it, and I should get 1. That make sense? That substitution right there allows us to generate that first Pythagorean identity that says sine squared t, or theta, whatever you want to use, plus cosine squared t is equal to 1. All right? And now why is it called the Pythagorean identity? We'll go back to that picture. Isn't this the right triangle? Yeah, that distance right there is cosine. That distance there is y, or sine. Cosine squared plus sine squared should equal my hypotenuse squared, right? That's where we're getting it. Or using this concept of substituting into that equation. So that's our Pythagorean idea. Now, there's a little bit of notation stuff here that I think is pivotal for us to understand. Sine squared t, that is the same thing as sine of t, the whole quantity squared. That make sense? If you write it this way, now some calculators understand this, but some don't. If I write it that way, what should be getting squared? The t, okay? And what happens, a lot of calculators understand that when you put those parentheses around that argument, and you put that power 2, that they understand that the whole thing in front of it is sine of t. Some calculators don't know that, though, okay? And sometimes, when I'm writing things, I'm lazy on my parentheses, and I'll just write sine of t that way, right? Well, if I put my power 2 there, now what is getting squared? The t. So to remove ambiguity, we put the 2 there. That make sense? Okay. It's kind of like when we had, radical 2 times x. Okay. It's the way we write it. We're uncertain of whether that x should be on the outside or should it be on the inside. So because of that ambiguity, we just traditionally write it out front, right? And now there's no question of whether it's on the inside or outside. So same thing with that sine squared, cosine squared thing. Now, in remembering the other 2, I'm not going to remember the other 2. I'm going to know the relationship that as long as I can divide by something here, it should generate these. So let's go through and divide everything by cosine squared t. Okay. Now, just a kind of a quick side note here, because I'm going to kind of glaze over this a lot this year. If I have sine squared t over cosine squared t, is that the same thing as sine of t times sine of t over cosine t times cosine t? Okay. Can I break those up into individual fractions? So what's sine over cosine? Tangent. And this one here would be tangent as well, right? So what's tangent times tangent? Tangent squared. So when I have sine squared divided by cosine squared, I'm going to ask what's sine over cosine, what's tangent. But because they're both squared, it's tangent squared. What's cosine squared t divided by cosine squared t? 1. What's 1 divided by cosine? Secant, so that's going to be secant squared. See how that automatically then generated that second Pythagorean identity? Okay. So if I think I'm going to need a tangent square, that I see a secant squared in an equation or something like that, I'm going to do that quick division. And now it's something, guys, I shouldn't have to write out too much, right? I should be able to say, I'm going to divide everything by cosine. Well, sine divided cosine tangent, cosine divided cosine 1 over cosine secant. And I get that real quick. What do you think I divide by to get the other one? Yep. Sine squared t, sine squared t, sine squared t. So that gives me 1. Cosine over sine, that is cotangent. And 1 over sine then is cosecant. Okay. So those identities, traditionally in a trig class, I think if you were to take this class out of the branch, they're going to give you that chart and say, learn it. They're going to tell you where this stuff comes from. And I think when they do that, you are at a disadvantage. You are being disserved by that establishment because there's reason for that stuff, and you need to know that reason because it makes it easier to understand if you know that reasoning. When you get to your homework, so last class we didn't do example 5, but we got to example 6. We only got 1 minute, so I'm not going to do it, but it's those questions where it says write tangent in terms of cosine t, and I've been wanting to do examples like this for the last 2 days now. Just haven't had time to get to them. I'm going to push back at some point. The assignment that's due on Monday, it'll be firm date Tuesday. Will be its due date. Yesterday I put 2 extra similar exercises on it, but we still haven't gotten. I think there's a handful of these on the end of that. I want to talk about 4 or 5 of them before you turn that in. But what this is, these are just generating additional identities, but they're identities that we don't use all that often. So sine squared plus cosine squared equals 1. We will use, in the course of this year, we might use that over 1,000 times. Okay, and what's left in the next 13 weeks. What you find out, that what you prove in example 6, that might be the last time you see that identity. So some identities are more important than others, so that's why we remember some of them, or they tell us to memorize some of them, and other ones we just work through and generate and then discard them. Okay, but a huge byproduct of working with identities is that you develop a very, very good proficiency and understanding of your algebra rules and skills in regards to manipulating things with algebra. Okay, so if you never do trigonometry again, or never going to see where you're going to use this stuff, an approach and visualize why we're doing this is to say it's going to make my algebra better. Okay, because at some point in your life, you're going to have probably kids, and they're going to be in Algebra 1, Algebra 2 class, and they might want you to help them, right? Well, if you suck at algebra, you're going to be able to help the kids, and your kids are going to say, well, my mom and dad's dumb. Okay, and you don't want that, right? Okay, so in the end result, if some of this stuff doesn't make, why are we doing this? View it that way, to help your offspring. Okay?
Teach your daughters how to do algebra and trigonometry.
Absolutely.